Welcome to lecture number 7 of my series on basic mechanics, a critical look. Let me quickly recapitulate the problem with which we ended the last lecture. This was a problem in which we had a boatman on a boat. The boatman's mass is m, small m, and the boat has a mass of capital M. The boatman is initially on one end of the boat, which is on a calm, quiet lake. And what the boatman does is that he moves over to the other side. Now, in the process of doing this, the center of mass of the man plus boat system shifts with respect to the boat. There is no external force on this whole system. So, with respect to an inertial observer, the center of mass behaves like a free particle. And since it was stationary to begin with, it will stay stationary throughout. So, in order to ensure that the center of mass stays at the same place with respect to the water of the lake, the boat has to shift the other way, to the left in this case, by small m over small m plus capital M into L. But, as we said at the end of the last lecture, there is a bit of a twist in the tail. And that is going to be what today's lecture will be all about. Near the end of this lecture, we will actually use some slightly more advanced mathematics than we have done so far, but it's not really very advanced mathematics. It's basically solving a first order differential equation. Now, even if you are not familiar with that, don't worry. Most of the important part of the lecture can be understood quite well without referring to that particular part. So let's get on with the lecture now. Now, in this particular form, this problem should be quite familiar. I'm pretty sure that many of you have already solved this problem as part of your course in class 11 or later. But there is a twist in this tale. So, let us now take a look at the boatman's tale again, but under slightly more realistic conditions. Here we consider, once again, a boat floating in a still lake, at rest to begin with, and the boatman, as before, moves from one end of the boat to the other end. But what makes this a bit more realistic is that we are going to consider a more realistic situation in the sense that as the boat moves on the water, it is actually subjected to an external force. A force which is going to resist its motion through the water, something which we call viscous drag, and this viscous force essentially is going to be proportional to the velocity with which the boat moves through the water. So in the real world, you will have this resistive force, and so we will have to use our second law of motion in the form where the external force is taken into account. So sigma mi ri double dot is now the net external force, which is no longer 0. And so if you denote the coordinate of the boat by capital X and that of the boatman by small x with respect to some common origin, you will end up with this equation. M times x double dot, small m times small x double dot, plus capital M times capital X double dot is no longer 0. It's proportional to capital X dot, the velocity of the boat through the water. The proportionality constant is something we have called alpha, and because this is resistive, this is of course going to be against the velocity, so you have a minus sign here. So this is the equation that the boat and the boatman, this combined system, is going to obey. Now let us see what this equation tells us about the final amount by which the boat is going to shift. That is, how much will capital X change when everything has settled down finally. Now, if we start with this equation and carry out a simple integration, I immediately get the following. Small m times small x dot plus capital M times capital X dot evaluated at small t minus the same thing evaluated at small t0 is simply minus alpha capital X at t minus alpha capital X at t0. where t0 is the initial situation and small t is any time in between as the motion progresses. Now, finally, what we will end up with is a situation where everything settles down. Small x dot vanishes, so does capital X dot. Neither the boatman nor the boat is moving. So the left-hand side vanishes because initially neither the boatman nor the boat was moving. Finally, also the same thing happens. So at this condition, when everything settles down, the left-hand side is 0. But that means that the right-hand side has to be 0 as well. And therefore, we will end up with the result that capital X at the final time, which may take infinitely long, so that's capital X at infinity, minus capital X at t0 must be 0. In other words, if you wait long enough for everything to settle down, capital X at infinity will be exactly the same as capital X at t0. So rather than shift by this to small m by small m plus capital M into capital L, as we had worked out before, the boat finally does not shift at all. But this does not really mean that the boat does not shift throughout. It actually moves, but it will always return back to its original position, which is quite different from the result that we had found out earlier. Now, you might, of course, not be too surprised by this, because after all, the two conditions under which the problems have been worked out are different. In the previous case, we had assumed that as the boat moves through the water, there is no resistive force. Here, we have assumed that there is a resistive force. So, the fact that the result in the two cases are very different should not at first glance be that surprising. So you might ask, exactly what is so surprising about this result? The point is, this result that we had obtained, that x at infinity, the position of the boat after everything has settled down, is the same as the initial position of the boat, happens to be independent of the value of alpha, the proportionality constant between the resistive force and the velocity of the boat. And that means no matter how small the value of alpha is, you are still going to get this same result. So if you take the limit of alpha going to 0, after you calculate the value of x at infinity, you will still get x at infinity equals x at t0. And this is what makes the result very surprising. After all, shouldn't the result coincide with the result that we had in our previous problem, where we did not have any resistive force whatsoever, in the limit alpha goes to 0? It turns out that if you take the limit alpha going to 0 after you calculate x at t going to infinity, that doesn't happen. You always get x at infinity equals capital X at t0. However, this previous result does emerge if you happen to take the limit alpha goes to 0 before you carry out the limit t goes to infinity. Then, if you had carried out this limit in the other order, you would get x at infinity minus capital X at t0 is none other than small m by small m plus capital M into L. Exactly the result that we had obtained previously. So notice that what we have is an example of something which is rather esoteric. A situation where the limit that we obtain after you take two limits, alpha going to 0 and t going to infinity, depends on the order in which the limits are being taken. This is an example of something which is quite common in advanced mathematics and not something that we find that often in physics, although we do find it in some rather important situations. The case of a singular limit, a situation where the order in which limits are taken determines the outcome. So, this very simple familiar problem actually has a rather surprising side to it. Something tells me that this should be a nice point at which we can stop this particular lecture. After all, we have had a rather surprising twist to a rather familiar problem, And that looks like a rather nice point for switching off. However, some of you may want to know a bit more about this issue of the singular limit in this particular case. If you are interested in that and not afraid to face a bit of calculus, a bit more calculus than a simple one-step integration that we had carried out a while ago, let us take a slightly deeper look in the rest of the lecture. Now, the important point is, we can figure out what is happening here by explicitly solving for capital X of t. However, how capital X actually depends on time t should depend on how the boatman is moving from one end to the other. And in order to understand that a bit better, let us take a look at the relative displacement, which we are calling xi of t. That's the Greek letter xi here, which is simply small x of t, the location of the boatman with respect to a fixed point, minus capital X of t, the location of the center of the boat. So this is really the displacement or position, really, of the boatman with respect to the center of the boat. Now, we can easily rewrite our equation in terms of small xi by getting rid of small x. That is, we just write small x double dot as xi double dot plus capital X double dot, plug that back here, and now you have small m plus capital M times capital X double dot, plus small m xi double dot is minus alpha capital X dot. And we can make this look a bit better by introducing some abbreviations. Small m divided by capital M plus small m, let's call that small mu. And alpha divided by capital M plus small m, let's call that beta. With these abbreviations, our equation takes a particularly simple form. Capital X double dot plus beta capital X dot is minus mu xi double dot. And it's obvious that we can immediately integrate this once to get capital X dot plus beta capital X dot equals minus mu xi dot modulo some constant of integration. We can make our life a lot easier by choosing our initial conditions so that at t equal to 0 minus, just before the boatman starts to move, capital X, the initial value of the position of the boat is 0. Xi is minus L by 2, which simply means that from the center of the boatman is on the other side, L by 2 distance to the left, and capital X dot and xi dot are both 0. These are the initial conditions which have been put in to arrive at this. Of course, you should also realize that we had been calling the initial time at which the boatman starts to move to be t0. We have now chosen t0 to be specifically 0. Simply to give the equation a slightly simpler form. Then, we can immediately carry out one more step. If you have any experience with the theory of first order differential equations, you would realize that this equation, especially the left-hand side, has an integrating factor. A factor by which you can multiply this equation, of course on both sides, so that the left-hand side becomes a derivative of t. If you multiply both sides by e to the beta t, the left-hand side simply would become ddt of capital X e to the beta t, and of course the right-hand side has to be multiplied by e to the beta t as well. Now this is your equation which can be integrated once again, rather trivially, to give you capital X of t e to the beta t minus capital X of 0 e to the beta times 0. You are integrating both sides of this equation from 0 to t, and of course capital X of 0 is 0, so that doesn't show up here, is minus mu integral from 0 to t of xi dot t prime e to the beta t prime dt prime. As you must have noticed, I have taken care of to label the dummy variable of integration as t prime rather than t. T here is the time at which we are evaluating capital X of t, and I have changed the dummy variable to ensure that no confusion between the two arise. And with this, we can write down a complete solution of our problem in terms of xi. Capital X of t works out to minus mu integral from 0 to t of xi dot t prime e to the minus beta t minus t prime dt prime. Notice that this is the full solution of the problem provided you know psi of t. You know exactly how the boatman has moved with respect to the boat. So the actual details of x of t is going to, of course, depend on exactly how the boatman moves from one end of the boat to another. Now, to be definite about our conclusions, let us talk of a particular case where we take a very simple form for psi of t. Psi of t is taken to be simply this, that is, the fellow actually moves with respect to the boat for a time capital T in total, and after capital T, he stays fixed at plus L by 2. So, the boatman is moving at a speed of capital L over capital T uniformly for a period of time given by capital T, in which he moves from minus L by 2 to plus L by 2 and stays put there afterwards. Note that all of this is the displacement of the boatman with respect to the center of the boat. So psi dot t simply becomes plus L by t between 0 to capital T and 0 henceforth. If you plug this into our formula, which needs only psi dot as a function of time, we end up with a simple integral to evaluate, which can be integrated very, very simply. After all, an exponential is one of the simplest functions to integrate, and after you evaluate the integral, this is what you end up with. And if you put back the value of mu, you get this form, small ml by m plus n, small t by t, 1 minus e to the minus beta t over beta t. All this is correct for t smaller than capital T. When small t exceeds capital T, you have to do the integration in two stages. You will get a value given by the integral from 0 to capital T, the same integral as the one before. But from capital T to small t, the integrand would vanish, so there will be no further contribution. So capital X of t will simply work out to be this. And therefore, this is going to be the final result. I have not bothered to explain all the nitty-gritty details of the algebra here. You can easily work it out yourselves. But let me just point out what this actually tells you about the nature of the motion. One thing you should notice, this beta is of course essentially the same as alpha. It's proportional to alpha. And in the limit beta goes to 0, this expression simply takes the form minus ml by small m plus capital M when small t is more than capital T. So once the boatman stops moving, capital X, the displacement of the boat, just take the value minus small m L by small m plus capital M. All this is where we have taken the limit beta goes to 0 first. Before small t reaches capital T, the displacement of the center of the boat is essentially proportional to the time, and that's easy to understand. We assume that the boatman is moving uniformly across the boat, and the boat is also drifting uniformly so that the center of mass stays fixed at all times. That is exactly what is going to happen when beta is 0. But more interesting is what happens when you take a value of beta which is very, very small. Here we have plotted the ratio of minus capital Xt by small ml by m plus m. This denominator here is the displacement of the center of the boat in the 0 beta case as a function of small t over capital T, and we have plotted this for different values of beta times capital T. Beta times capital T, as you can easily check, is the relevant variable here. Because of the minus sign here, a positive value for this variable means the boat is drifting to the left. Now, for a rather large value for this parameter small beta times capital T, you see that the graph essentially keeps on rising somewhat like linearly at the beginning, but then reaches a maximum, which is only 60% of the full displacement would have happened for 0 beta, and then exponentially decays down to 0. The same thing happens for a slightly smaller value of beta capital T of 0.5, but now the motion essentially reaches a slightly larger final limiting value. After that, it starts decaying a bit more slowly than before. If you start with a much smaller beta capital T of 0.01, the motion is almost linear until it reaches a peak which is almost minus m capital L by small m plus capital M. And then the decay, which is actually exponential, is so slow that it looks like a very, very slow linear decay. So this is also going to decay to 0, but it's going to take a long time to decay. Notice the same thing can be said if beta t is taken to be even smaller at 0.001. Here, the value that is reached at small t equals capital T is actually almost exactly minus ml by m plus m. After that, the displacement decays, but does so very, very slowly. There's the orange line on top, which is almost horizontal. Now, notice that as long as there is a non-zero beta, the displacement always decreases to 0 if you wait for long enough. However, if beta is very, very small, then for any reasonable amount of time, you will essentially see very little decay after the boatman has stopped. So the singular limit does tell you that you have two entirely different situations depending on whether beta is going to 0 is taken before or after t going to infinity. But you have to also realize that as beta is made very, very small, the 0 beta result, which is a linear rise to the final value and steady at minus ml by m plus m from there, is not very different from what you get for very small beta. You get the almost linear rise for very small beta and an almost steady value after that. Now, I hope this example has made it possible for you to understand exactly what is going on with the singular limit that some of you may have met for the very first time. Singular limits, as I have already said, is very, very important in physics. They crop up in very important physics situations, like in phase transitions. I hope this example from elementary mechanics gives you some insight into the kind of mathematics that really leads to such limits. In the next lecture, we will return to the other way of writing Newton's second law for a system of particles, the way which involves the rate of change of momentum, and take a look at its physical consequences. Bye till then.